Hello, my name is Rodrigo Aldana, and I'm a PhD student at the University of Zaragoza. Today, I'm presenting the work EDC, which stands for Exact Dynamic Consensus. As an outline, first I'm going to present the problem statement, which is a version of the dynamic consensus problem. Then, I'm going to give just a quick preliminary on graph theory, particularly for notation. Moreover, I will inspect some of the previous solutions to the problem, and I will motivate what can be improved. Additionally, I will talk a little bit about an important ingredient, which is the exact differentiation techniques. Then, I will talk about our solution and some of its properties, which makes this solution admissible for the problem. Finally, I will show some simulations and I will draw some insights about the future work. In the problem setting, we have a set of nodes and a set of edges which connect the nodes, forming a connected network. This network represents the communication graph between nodes, which we will label with numbers for convenience. Then, focusing to a particular node, it has access to a time-varying signal as the one shown here. It has an output yi and an internal state xi. The evolution of the internal state is governed by a differential equation, which will depend only on local information. This is the local internal state, the local signal ui, and pi, which stands for the messages other agents share. The goal is that for a set of time-varying signals, the nodes are able to compute the average of them, which is a global quantity, even though they only have access to local information. Concretely, the output of each node must approach the average as time goes by, formally stated with this limit. In this context, the following questions arise. How to design the evolution of the internal state, and what should the agent share? As a quick reminder of graph theoretical notation for networks, a graph can be represented by its adjacency matrix, in which each component contains the information of whether two nodes are connected or not. Another important object is the incidence matrix, which has a column per edge in the network. The 1 and -1 elements represent the two endpoints of the edge. In this work, we consider undirected networks, so the ordering of the 1 and -1 is arbitrary. One important property of the incidence matrix, which we will use later, is that if we multiply it from the left by a row vector full of ones, represented with this symbol, by construction we will always obtain 0 as a result. The Laplacian of the network has the number of neighbors of each node in the diagonal, and the negative of the adjacency matrix in the off-diagonal. One important property of the Laplacian is that it can be factorized in terms of the incidence matrix, as shown here. The typical solution to the problem is the following, based on a linear protocol. Each node has its output defined as the difference between the signal ui and the internal state. Moreover, the state evolves according to differences between its output and the neighbor's output, which they share. Note that this summation goes only through the neighbors of the ith node, by means of multiplying by the adjacency matrix components. By stacking all node states in a vector, denoted by capital X, we can write the evolution of the whole network as follows, using the Laplacian matrix and the vector of outputs denoted by capital Y. Writing the top equation in this notation with the vector of signals as capital U, we arrive at the compact representation of the protocol for the whole network. In order to see how this protocol works, let's differentiate the top equation and substitute the dynamics of X. We arrive at a linear system, which would be stable towards consensus with positive kappa, if it wasn't for this term, which acts as a disturbance. If the derivative of U vanishes at infinity, then this protocol solves the problem. However, if the derivative remains bounded, then the outputs will reach only practical consensus with bounded steady-state error. Take as an example the following set of signals for which their derivative doesn't vanish at infinity but remain bounded. This is the evolution of the protocol in a network of 10 nodes. Note that the output stays together after a transient, but never converge towards exact consensus. This can be shown by looking at the error they have with respect to the average of the U signals, which shows a bounded steady-state error. Exact consensus may be reached by means of factorizing the Laplacian in terms of the incidence matrix, but fitting a nonlinear function in between, maintaining the distributed nature of the protocol. If this function is chosen to be discontinuous, as this one, where we only use the sign of each component of the input vector, We recognize from the sliding mode control techniques that for sufficiently high gain kappa, the correction term can induce robustness against the disturbance if it remains bounded. The following is a simulation of the same scenario as before, but with a discontinuous protocol. Note that exact consensus is reached in finite time. However, in this simulation we used a small time step. It is known that for large time steps, a first-order sliding mode will induce non-smooth signals as a result, which may not be useful in practice. From this formulation we ask, what if the derivative of u has no known bound, but a high-order derivative has? Moreover, we ask if we can leverage high-order sliding modes to help with the disadvantages which arise from first-order sliding modes as we saw before. Our solution is inspired by the structure of the exact differentiator of arbitrary order, which I will take a moment to review. It assumes that there is a function f, for which we want to obtain its derivatives, and has an n+1 derivative bounded by a known constant L. The system contains correction terms which depend on the difference between the first state and f. And it can be shown that for some properly chosen gains, this error can be driven to zero, which means that the first state tracks exactly f. Under this condition, all correction terms, except for the discontinuous one, vanishes. This leaves an integrator chain, which from the condition that the first state tracks the signal f, then each other state tracks a different derivative of f. The reason this works can be shown by making the change of variables in terms of the errors, leading to this system, with a bounded disturbance in the last state, which can be rejected by the discontinuous correction on the right. Now we are ready to present our solution, which has the following form. Each node has a vectorial internal state xi of dimension n+1, instead of a scalar as before. Our system contains correction terms inspired by the ones of the exact differentiator, as well as an integrator chain. However, we inherit structure from the dynamic consensus protocol by using information of the neighbors only, and by making corrections in terms of the outputs, which are defined as the difference between the time-varying signals and the internal state, as before. However, note that the output is only computed using the first element of the internal state. Hence, all nodes share only a scalar, similarly as before. This protocol can be written in compact representation by defining these vectors. Capital X by stacking the element mu of each node, and capital U and Y naught by stacking the signals ui and the outputs in vector form respectively. Moreover, define this nonlinear function which computes the powers we saw before in the protocol for mu less than m. Note that these functions are all continuous. Similarly, we define this discontinuous function. Recall that m is the dimension of the internal state minus 1. Using this notation, our protocol can be written as follows. Now, to explain intuitively why this protocol works, let's extend the definition of the vector y to y sub mu, defined as the difference between the muth derivative of u and x sub mu. By inspecting how this new variable evolves, we arrived at this expression. Note that the n+1 derivative of u appears as a disturbance. However, the discontinuous term in the last equation can reject it as long as it remains bounded. Formally, it is only required that the differences between the n+1 derivatives of each signal remains bounded. But, for the sake of simplicity in this presentation, let's consider the first case only. Another important assumption, which we will consider at the moment, is the following. We assume that the initial conditions of the system are such that the mu elements of the internal state of all nodes in the network add up to 0. This is a standard condition other methods in the literature have, and can be weakened by means of additional techniques. It can be fulfilled trivially by making all internal states start at 0. This does not mean that we start at consensus, since the initial condition for the signals ui may be different between nodes. Moreover, this condition can be written compactly as follows, where we used the vector of ones. Now, we are ready to state one of the main properties of the protocol, which states that under this assumption, such condition is not only fulfilled at the beginning, but is maintained at all times. Let's take a look at the proof. We start by defining the quantity of interest as the scalar function mu. For the proof, we will proceed by induction. First, let's focus our attention to the last equation of the protocol, the discontinuous one. Now, we can multiply by the left by the vector of ones, obtaining how Sm changes. Moreover, note that the product of the vector of 1s and the incidence matrix is always 0. Then we obtained that Sm does not change and therefore is maintained at 0 at all times. Next, induction will follow from m to 0 by assuming that the mu plus 1 condition is fulfilled. Let's inspect the mu equation of the protocol, and similarly as before, multiply by the vector of 1s from the left, obtaining how S mu changes. Note that the first term vanishes due to induction, and the second one vanishes due to the same property of the incidence matrix we used before. Therefore, since S mu does not change, it will remain constant at 0 at all times. This property will be important for the next result. We want to inspect if the protocol in fact reaches consensus to the average of the time-varying signals Ui. Let's take a look at the protocol again and see what happens after the transient. If the protocol converges, these correction terms will vanish, meaning that the vector y0 has components all equal to each other. In other words, y0 will be equal to a function alpha times the vector of 1s. Now, the next question arises. What is this function alpha equal to? I will now show that after a transient, alpha will in fact correspond to the average of the time-varying signals. Let's take a look at the proof. Start with y0 and multiply with the vector of 1s and divide by n, where n is the number of nodes. Note that the scalar product of the vector of 1s by itself is in fact n. This leaves only alpha. Now, expand y0 by its definition, leaving these two terms, where the second term vanishes due to the lemma we showed before. This leaves us with the conclusion, which is that alpha is the average of the time-varying signals. However, we can make a stronger conclusion here, and is that if we take a look at the vectors y mu we defined before as the difference between the mu derivative of u and x mu, then these vectors will converge to the derivatives of alpha. In other words, we are able to track the derivative of the average of the time-varying signals too. And the proof is the following. From the protocol, we obtained this expression of the evolution of y mu, but since y0 is a multiple of the vector of 1s, the correction terms are cancelled, leaving us with the integrator chain from which we obtain that each y mu is the derivative of the previous one. Let me summarize the properties and assumptions of the protocol so far. Our protocol has a vectorial internal state, which is characterized by the order of the protocol M. Moreover, we assumed that there is some boundedness condition of the m plus 1 derivative of the time-varying signals we want to track the average of. Moreover, even though the nodes have an internal vector state, they only communicate a scalar, namely the difference between its local time-varying signal and the first element of its internal state. If the protocol starts with an internal state orthogonal to the vector of 1s, it will remain as such at all times. Furthermore, if the protocol converges, it will converge to a point in which the outputs of all nodes track the average of the time-varying signals, without a steady-state error. But not only that, the derivatives of such average can be easily tracked too, without communicating any additional information. To the best of our knowledge, this is the first method which achieves this. And finally, the property which we will show in a later work is that there exist some properly chosen gains such that the protocol converges in a finite time. Now, let's take a look at some simulations of this protocol. In these examples, we used 10 nodes connected in this topology. Moreover, we used m equals 3, which means that the internal state of each node has a dimension of 4. These are the trajectories that the output of each node follow. We used some properly chosen gains such that the outputs of each node reach exact consensus in finite time. In other words, to ensure that the transient ends at some point. As we discussed earlier, the design procedure for the gains will be described in a future work, since it's not trivial. Here, we show the error of each node with respect to the average. Note that the method obtains smooth signals after a transient, even with the same change in the time step we saw before. Now, inspecting the protocol a little bit closer, let's take a look at the proof y0, y1, and y2, and note that they reach consensus towards the mean of the signals, the mean of the derivatives, and the mean of the second derivatives. Moreover, if we expand the definition of these vectors, we see that in order for the agents to compute these quantities, they must have access to the derivatives of the time-varying signals. However, this can be computed locally by means of an exact differentiator. There are still some aspects of this protocol which we will show in a later work, due to space constraints. The first one is how to weaken the assumption on the initial conditions, since we'll break easily when nodes connect or disconnect. The second one is how to choose the gains of the protocol in order to ensure stability. This procedure is not trivial. However, we have interesting answers to these questions, which will be presented elsewhere. And that's it. Thank you all for your attention. I'll be happy to answer any questions you have.